determining if something is ionic or covalent? Look at the first element. If the first element's a metal, then you know that it is ionic. So first one, calcium sulfide, it is ionic. Because we have the metal, that's going to make it ionic. So we know this one's ionic. So calcium's symbol is Ca, and the charge +2. And remember, you know the charge on the metal because it is the group number. Second column, so it's a +2. With ionic, you got to assign charges. Sulfide is a symbol, just S, not SO4, that's sulfate. So sulfide is just the S, it's in group 6. So remember with the nonmetal, it's how many does it need to make 8? That'll be its negative charge. So 8 minus group 6 would tell you that it's a -2. Okay, so there's the charges. So now how do you figure out the formula? Just do the swap. So the charge on the metal tells you the number of nonmetals. Charge on the nonmetals tells you the number of metals. So Ca2S2. And the last rule, you want to simplify. So since they're both 2, you can divide both by 2 to make the simplest combination. Just 1 calcium per 1 sulfur. Chromium 2 nitride. Chromium is... Oh, well, you know this is what? Ionic or covalent? Sorry. It's ionic because chromium is a metal, right? So if it's a metal, then you know it's ionic. So in this one, Cr, what does that 2 tell you? That it's a +2 charge. So that Roman numeral tells you the charge because chromium is one of those that could be a +2 or a +3. So just look at the Roman numeral to figure out the charge. And then nitride is a... It's N and it's -3. So you see that it's in group 5. 8 minus 5 is 3. That tells you the charge of the nonmetal. This one, when you swap, what do you end up with? Other way. Remember, swap the opposite. So the charge on the chromium tells you the number of nitrogen. The charge on the nitrogen tells you the number of chromium. So it's Cr3N2. And you don't simplify that. That's as simple as you can do it. Sulfur dioxide. It's covalent. Because sulfur is to the right of the zigzag line. It's a nonmetal. So if it's sulfur dioxide, its formula, yeah, just SO2. So remember with covalent, when it's just a binary compound, covalent, you're going to know the number of each atom. Na2CO3. It's ionic. So Na, sodium, CO3, carbonate. So remember that if you see a carbon with an oxygen, with a bunch of oxygen, sulfur with a bunch of oxygens, nitrogen with a bunch of oxygens, that's those polyatomics. Okay, so that's definitely maybe one that you got to put on your card. Those 7s, what their charge is and what their name is. So that's sodium carbonate. So 4.5 moles of CH4. We want to know how many grams. If you see moles and grams, what do you need to find out? The formula mass. So if you see moles and grams, you want to figure out the formula mass. 1 carbon, how much does each carbon weigh? 12. So look on your periodic table, take the mass and just round it. 4 hydrogens, and each one weighs 1. So 12 and 4 gives you 16 grams is equal to 1 mole. So to do this, you just take what you're given, times in a line. What unit goes on the bottom? Moles is going to go on the bottom. Grams is going to go on the top. It's just a single step. That's all you have to do. 16 goes on the top. 1 goes on the bottom. 16 grams in 1 mole. And you end up with 72. That one's nice. You don't have to round it. 4.5 is two significant figures, 72 is two significant figures, so you would just leave it as it is. But if you have moles and molecules, then what you have to use? Avocado's number. I've heard that before. It's not the first time. Avogadro's number, and that is 6.02 times 10 to the 23rd molecules is equal to 1 mole. So you don't have to do any calculations like figuring things out. You just have to use that number. So in this, 4.5 moles of CH4 times in the line, what unit goes on the bottom? Moles. Molecules will go on the top. Sorry, I just said what I was thinking. 1 in 6.02 times 10 to the 23rd. Key thing in this, just make sure you put it in your calculator right. That's really the big reason why people get this wrong. So you take 4.5 times 6.02 EE23. If you have a graphing calculator, oftentimes you have to put it in brackets in order for exponent numbers to end up being multiplied and divided correctly. So do kind of double check that. Not so much when we're just got 4.5 moles, but if you had two molecule numbers, and so you ended up having to divide, like if you had molecules and you were going to moles, you put molecules on the top, put Avogadro's number on the bottom, and in that case, you want to make sure that you put those brackets in. If you use the EE button, then you don't have to. It's not a problem. So 4.5 times 6.02 EE23. So I got 2.709? Nope. Okay, well, hold on. Maybe I did it wrong. Times 6.02 times 10 to the 23rd. Nope, I got 2.709 times 10 to the 24th. Yes?
I don't know if I'm putting it in wrong.
Okay, let's try it again. Show me what you're doing. So clear it. 4.5. Oh, you put 4.8. Yeah. 4.5. Oh, maybe that's why you're getting it wrong. Yeah, because you wrote 4.8 down. Try that.
4.5
times 6.02.
Yep.
Okay, so you got it right. Okay, so in that, 4.5 is two significant figures. So what do I have to do to that number? So it would be just 2.7. You do have to keep the exponents. Okay, so do keep the exponents. That's not a significant figure. That's just showing how big the number is. So remember on your calculator, when you see those little digits kind of raised slightly, that's that exponent value that you have to go back and put in. Okay, so these last ones are looking at shapes and we're thinking about polarity. So in this one, pH 3, so you see that it's a covalent molecule, phosphorus and hydrogen, nonmetals and hydrogen that are there. So what's its ABN? That's the VSEPR. What would be its ABN? Not just N, because it's pairs, right? Okay, so remember that it's A would be the phosphorus, B is that it has 3 things connected to it, N would be that it's got 1 pair of non-bonding electrons. And whenever you see that, the shape is the pyramidal with nitrogen. Whereas oxygen, being the central atom in this, what would it be, polar or non-polar? Okay, so do you see a nitrogen, oxygen, fluorine, or chlorine? No. So if you don't, then it is non-polar. The only time it's going to be polar is if you have a nitrogen, oxygen, fluorine, or chlorine, and it's only like on one side of the molecule. H2O, the VSEPR for the oxygen would be AB2N2, and they call that shape bent. Water is always bent, and it's very. And so that side over here becomes negative. This side over here becomes the positive, creates that imbalance. Water is an extremely polar molecule. The carbon in CO2 though is what? AB2. Does carbon have any non-bonding electrons? No. The oxygens do, but that's not the one you're looking at. You're looking at just what's around the carbon. So you would say the carbon is connected to two things. So even though they're double bonds, it's just one connection. So that's AB2. And so when you have that, they spread straight out 180 degrees apart, and you call that shape linear. So is it polar or non-polar?
No.
It's non-polar. You have oxygens, but the oxygens are on opposite sides and they balance each other. So the only time it's going to be polar is if you have a nitrogen, oxygen, fluorine, and chlorine, and it's on one side. It's like on one side of the molecule, whereas that one, can you see how they're balanced on either side? So that's going to be a non-polar. All right, so we'll try and do another one of those again next week. I'll make up another one because this kind of really like summarizes a whole lot about chapter 3, just this one slide. So going back, look at this. So these are, not these things, I don't know what those are, but the rest of it, 3 molecules. See if you can tell me the name. This is what we were doing last time, looking at naming and going through the steps. So do each one of those, and then we'll come back and talk about them. So I just rewrote sort of like the 4 steps. That's what you want to do with all of them, just these 4 steps, and do them in order. First, find the longest carbon chain, circle it. That becomes the last part of the name. So in the upper one, what is the longest carbon chain? 7. Now, it would be fine if you went straight across. Do you see 7? Okay, but you could go like this. Do you see 7? Yeah, it's all the same. You could even do this. Do you see 7? They're all the same. It would end up being the exact same name. Okay, you would end up with the exact same name no matter how you circled the longest carbon chain. But the longest carbon chain in this one is this 7. So I'll just go stick with the straight across because it's simplest when you look at it. So 7 is a what? Yeah. She got the last name. So that's like 1 point because these are always worth like 3 points. So if you circle and tell me the longest carbon chain, if you can't do the other things, you'll stay at a point. Next one, step 2, circle and identify any non-hydrogen groups that are not part of the chain. So in this one, there's 2. So this is a CH3. It is a methyl, even though I can't write. methyl. So remember, one carbon is meth. When it's hanging off, it's a methyl. The other one, though, is a CH2CH3, so that is a ethyl. Okay? Now I got a number. Which side does is closest to the first non-hydrogen group?
So
The left. That tells you how to number. So what you can do is you can just start at the end and you just start coming in. First non-hydrogen branch you come to, that tells you which side to number from. If they come at the same, then look and see if there's any others, like what is the number combinations. Otherwise, it's just a picking kind of thing. So we're going to number from this side. 1, 2, 3, 4, 5, 6, 7. Okay, so that means that our methyl is hanging off of carbon 2, and that the ethyl is hanging off of carbon 5. That's what the number in front tells you. Okay, so the number that you write, you don't have to write out the word 2 or the word 5, you just use the number itself, and it's telling you which carbon on the chain it's hanging from. If you went to draw this, it would be fine if you had the methyl group sticking up, as long as it's on carbon number 2. It'd be perfectly fine if you drew it the opposite direction and hung your methyl group off of the second carbon from the right, as long as it's on carbon 2. Okay? But like, this is just way faster for me to grade if it looks like that. Just gonna say. Last step, you list them alphabetically. If you have any common groups, you group them together. So if you had 2 methyls, you would call it a dimethyl. If you had 3 methyls hanging off the chain, you would call that a trimethyl. But these ones, we have a methyl and we have an ethyl, so you're gonna list them separate. But which one do you list first? So it's 5-ethyl, which seems backwards because you would think you'd number it by the carbon, but no, you number it alphabetically. I didn't make the rules. So ethyl E becomes before M, so you would put ethyl first, methyl second, 5-ethyl 2-methyl heptane. So when you see this ring, you know that this is a what? That it's a cyclo something. So the last name is the number of carbons in the ring. So this is a cyclohexane. Count them, 1, 2, 3, 4, 5, 6 carbons. So that means just saying cyclohexane has taken care of all those carbons. So I don't have to name them separately or anything. They're part of that ring of 6. So that is step 1. Step 2, any non-hydrogen groups hanging off, and it's an ethyl. It's a 2-carbon group hanging off. That is an ethyl group. Numbering, when you have a ring, always start numbering at the first non-hydrogen group. Okay, and this one, there's only 1, so that makes it super easy. We're going to call that the 1. In fact, most of the time, they'll leave that 1 off. They'll just call this ethyl cyclohexane because there's only 1. So no matter where you hang it, it would always be on carbon number 1. So ignore these funny little squiggly things because I don't really know how they got there. But the rest of this, longest carbon chain is an octane. So you see this? If I went this way, how come this isn't right? Because how long is that? It's only 7. So that's not long enough. So you want to find the longest carbon chain. So this makes it a octane. So that means that I need to name this and this. So the top one is a methyl. The bottom one is a Now which way am I going to number, from the top or the bottom of my chain? Top, because you see the methyl group is 3 in. If I come from the bottom, the ethyl group is 4 in. So I definitely want to start from the top. So that makes your methyl A 3 and makes your ethyl A 5. Ethyl, 3-methyl octane. Now, when you are doing your MyLabs Plus and they ask you to do the naming thing, they don't like any spaces. So if you have a space between a number and a letter, like 5, and there's a space before ethyl, how they like you to do it is they like you to put a dash. So they like you to put a dash after a number before the word. They like you to put a dash after the word before the next number. So, and methyl octane would all be one word. You wouldn't leave a space between methyl and octane. So the last non-hydrogen group kind of gets like sandwiched in with the last name. So ethyl cyclohexane, this one, you would just write that all as one word. Okay, you wouldn't have ethyl space, it's just ethyl cyclohexane. In the books, you have like 3 chances, and it will actually come back and say, go back and put dashes. That you have to put dashes between your things. It'll come back and give you that as a hint. But that's just so that you don't have to do it. Just make sure no spaces. Now, if you had like 1,1 dimethyl, then you put 1, 1 dash dimethyl. So you put a comma if you have multiple non-hydrogen groups where you have to indicate multiple carbons, which ones they're hanging off of, you use commas in between. I don't care. Like, I'm not going to mark that wrong. If you name it and you don't put a dash, that doesn't bother me. But in terms of like getting your answers right in MyLabs Plus, they'll be like, no, you have to go back and make sure you put those in. So I'll just tell you that to make sure you do those. All right. So we got those. Remember with skeletal structures, in that first one, how many carbons are in that upper left structure? 6. So everybody see that. So we have 1, 2, 3, 4, 5, 6. So that makes this chain it's a hexane. So when you start numbering, and I oftentimes will go back and put dots in my corners and ends to help remember those are carbons. So when you would start numbering from this side. So what's that hanging? What's this group? That's a chloro, and it's on carbon 2. So this one would be 2-chlorohexane, no spaces. Remember, though, that those carbons all have hydrogens, but you don't have to go back and name those. But if you have ones that are hanging off like this, how many carbons in this molecule, the one that's over here in the upper right?
3, 2, oh.
How many total?
10.
Nope.
8, 11.
Yeah. There's
8. Yeah.
Well, there's 8 in the chain, but how many total? How many carbons total?
Oh, 11.
Can you see that? Okay. So every end, 1, 2, 3, 4, 5, 6, 7, 8. That's the longest chain. But then this is a carbon, this is a carbon, this is a carbon. So if you have just a stick hanging out, what is that group?
It's a ethyl.
Nope, just a single carbon, so it's a CH3. It's a methyl. Okay, so a single line sticking off of your chain on a skeletal structure, this would be a methyl. So we said it was 8, so that's octane. So that means that this is a methyl and this is a methyl. Which way do I number from? From the right. So remember, start numbering from the very end because that's a carbon. 1, 2, 3, 4, 5, 6, 7, 8. Right?
So we do 2, 3, 4, 5.
Yeah. 2, 3, 4 dash tri methyl octane. You have a methyl on 2, a methyl on 3, and a methyl on 4. But if you see this, this one down here, 1, 2, 3, 4, 5. So this longest carbon chain is a pentane. But now this group hanging off, that's an ethyl. Can you see that this is a CH2 and that's a CH3? So that one would look like 2 sticks coming off. This is an ethyl. Yep. And it won't get any harder than this. They're going to look like these, okay? So you'll just have the chain and you'll have a couple of them hanging off. You just have to figure out which way to number, list them alphabetically. But sometimes I've had people miss these because when they look at that stick hanging off, they want to call that a hydrogen. You know, I don't know why, but if the stick is hanging off, there's always a carbon on the end. If you have a skeletal structure, there's always a carbon on the end. But notice this one right here, at the end of that is a bromine, so that's not a carbon. So this is just a bromine sticking off of that carbon that I put the circle. Like the one up there, that's a chlorine sticking up, that 2-chlorohexane. So if you do have a bond coming off of the chain, and it's got a halogen on the end, then that's all it is sticking up there. So this one's 1, 2, 3, 4, 5, 6, 7. There's 8. So, right. And so then you say, okay, this is a what? That's a bromo, and this is a methyl. But the longest chain, 1, 2, 3, 4, 5, 6, 7, 8, is the octane. So this is what makes it octane. Is that 8 in a row. And then you're just going to name anything that's hanging off on the skeletal. If just a line's hanging off, it's a methyl. If there's a line hanging off with a chlorine, though, that's a chloro. So B3. I'd start from the left, because it'd be 3, 4, 5. Because if I started from the other side, it would be 4 and 6. Like I said, that's why I go back and put the dots. Like I'll go back and put dots on all of my skeletal structures to make sure that I'm actually not missing a carbon accidentally, skipping one, missing one that's on the end. Because people do really much better with the Lewis structures and with condensed. But when they see a skeletal structure, I don't know why they just want to leave off carbons. Like it's happened very many times that I've had this. That I'm like, well, what was that line hanging on? Like, I don't know, I thought it was a hydrogen or something. So like that's a common mistake. So that's the one just to make sure that you remember every corner and every end is a carbon, unless you have a halogen listed. So you're feeling better about them? Okay, so in this, I think this is easier. It's easier to draw a structure from the name than it is to figure out what the name is from the structure. Because in this, what do you do first?
You go from the last.
Yep, find the last word. And that tells you the longest carbon chain. I like to just lay down my carbons and then I'll fill it in afterwards. So if I see hexane, how many carbons in a row? No, 6 hexagons. So 1, 2, 3, 4, 5, 6. Then you can number, and you get to choose. You can number left to right or right to left. I just go left to right because that seems more like a sentence kind of way. So then the next thing is I have a 2-methyl. So what am I going to put? And it wouldn't matter if you put the CH3 down or the CH3 up. You could do either. You don't even have to make your chain straight. It's just like, to me, it's easier to look at it if it's like laid left to right and everything's straight. Huh? That's right. So as long as you drop a CH3 or connect a CH3 to carbon number 2, then that's a 2-methyl. Okay, so then the other one? Where? Yeah. So you could put the chlorine up. I put the chlorine up because there's a little more room up there. You wouldn't have to. You could put the chlorine down. All that matters is that it's on carbon number 3. So this carbon number 1, how many hydrogens will it have? It's going to have 3, right? Because it doesn't have anything. It only has connected to a carbon. So it's going to have 3 hydrogens there. So if you were going to do as Lewis structure, you'd say that one's CH3. How about carbon 2? How many hydrogens does it have to have?
4.
It has to have 4 bonds. How many do you see connected to carbon 2? Carbon 2 has 3 bonds connected, so you know that's going to be a hydrogen up here. So that's a CH. So then a CH3 hangs off. And then the next one, that next carbon, the one with the chlorine, so it would just be an H, because you can already see it's got 3 bonds. So it would have to have 1 more to make 4. Okay, so you would always have, so the next one would be CH with the chlorine up. But what about 4? Carbon number 4 in the chain has 2, so how many hydrogens? So that would mean that there's going to have to be a hydrogen above and below. Carbon 5 is a CH2, and then carbon, the last one, would be a CH3. Okay? Mm-hmm.
So what's the difference between the top and bottom?
So the top one is really just kind of like building it. If I was going to draw the condensed, remember this would be considered the condensed structure. The condensed structure lists each carbon and how many hydrogens or what bonds are connected to it. Now, if I was going to do the Lewis structure, I'd have to put all the lines in. So every line, like every carbon would have to have 4 lines, and you'd have to see the hydrogens, and they're each one a single line. Condensed, you don't have to put all of the lines. In fact, I shouldn't have put this one in, but I just start doing that when I build my chain. But what if I was going to do the skeletal? How many zigzags would you put? 5. 1, 2, 3, 4, 5, 6. Right? So remember, when you're doing skeletal, if it's hexane, that's 6, and so it's 1 less line, because all you're seeing are the bonds between carbons. Okay? And so then what would you do? Which would look like a line. So you'd have a line. There, CH3. So that line sticking up is a CH3. And then what else? So then I'd have a line and a Cl sticking down. So if you just have a line, it's a CH3. But if you had a line and a Cl, that just means there's a chlorine off of that
So
one.
what if we do that and we write we do the line, but we write CH3 on the side of it? That wrong?
Well, if you were doing a strict skeletal structure, you never see carbons.
Okay.
Okay? So strict skeletal structures, you don't have any carbons on there. It's just listed like that. The only thing that you would actually write out would be any halogens. Chlorine, fluorine, bromine, iodine, you would have to put those, because those aren't just carbons and hydrogens. So you can see why some people really like those, because they're so much faster to be able to draw. You just do some zigzags and slashes and move on. Okay? What about this one? 3,4-difluoro-7-ethyl-decane.
9.
Decane.
10.
10, yeah. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So if I was going to do a Lewis structure, I'd have to have all of these. Which is why I don't like Lewis structures. Right? Because every single carbon is going to have 4 bonds. To put the pieces in, carbon 1, carbon 2, 3, 4, 5, 6, 7, 8, 9, and 10. What can you do next? Put a fluorine on 3 and a fluorine on 4. It would be fine if you put them both pointing down, both pointing up, one pointing up, one pointing down. Doesn't really matter, because remember that the single bonds have that rotation ability. And then the last one, CH2, CH3. Sometimes you'll see CH2, CH3s written like that, like coming straight down off. You could also potentially see it pushed down a little bit further. So they'll draw it like this and then go CH2, CH3. Same thing. Okay? It really just depends on how much room you have. Just so long as you have a CH2, CH3 hanging off. And I wouldn't mark it wrong if you wrote it sideways. I wouldn't care. But all the rest of these are, ugh. So if you're going to do the zigzag, how many zigzags? 9. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. See how much faster that was? And if you went back and did that condensed structure, you would say just put each carbon with how many hydrogens around it, if you wanted to simplify it a little bit more. Sticking off of carbon number 3, so this is carbon 1, 2, F, and then looking upwards would be another F, so that's 4, 5, 6, so then 7 would look like that.
I need all skeletal on test.
There's a couple where I'm like, give me the condensed structure of, and then a couple where I'm like, give me the skeletal structure of. So there's a few where you have like to do different ones. All right, now, so we've gotten these, blah, blah. There are groups of molecules that can have the same formula, but may look different and may actually have a different bonding arrangement. So those are the isomers. So if you're in lab, you had that experience of doing and talking, starting up talking about isomers. Not super difficult. Just remember that isomers have the same formula. So if I have C4H10, that's butane. And if I draw it out as butane, 4 carbons, end carbons have 3 hydrogens, middle carbons have 2. Right? If we just draw it out in that Lewis structure. So is this structure the same or different? Why? Okay. What's its name? What's the name of the second one? What's the longest carbon chain? Okay, so it is butane. So when you first look at it, do you think like because it's got this bend, then you're like, is that like the same? Well, remembering lab, like in terms of their 3-dimensional, the carbons really make this zigzag arrangement. And so they rotate around. That one was the one we actually did like a zigzag and we flipped it around and made it look like a little cup. Okay, so we could turn it around this way or turn it up this way. So those two, when you initially looked at them, you might have been like, oh, they're 2 different molecules, but they have the same name. Those are the exact same molecule, just drawn differently. Those are conformational isomers. They're the same molecule, they just look different because of how you drew them. And the trick with this is if you name them and it's the same name, it's a conformational isomer. So you could even see one drawn this way, straight up, straight down, straight up or straight across, but still 4 carbons, 10 hydrogens. So that's still 4 carbons in a row, it's still butane. It's butane, just looking at it in different ways. Same formula, same name, conformational isomers. But look at this one. I can't erase it. There's butane, 4 carbons in a row, all in a straight line. But then look at the next one. The next one over, we only have 3 carbons in a row and then a carbon hanging off of the second carbon. So the longest chain in this one is propane. And the group hanging off is a CH3, so it is methyl. So this would be 2-methylpropane. So those two, and we actually did this in lab, the one that looked like the zigzag and the one that looked like the Y shape. So these two, the only way I can change from one to the other is I'd have to pull things apart. I would have to break bonds and make it back into the straight chain or to make that branch chain. So these are structural isomers. They have the same formula, but they have different names. They have different names because the molecules put together differently. You can't flip one around and turn it into the other. You have to take it apart in order to change it from one form to the other. So structural isomers have same formula, but different names. They have a different bonding arrangement. And in fact, so they're really quite different molecules. They may not behave exactly the same way. They may have different physical and chemical properties. So the key to figuring out if one is one or the other is you just name the two. Just name each isomer pair. If they have the same name, you know it's conformational. If they have different names, then you know that it's structural. C5H12. If you were going to draw a molecule that had 5 carbons and 12 hydrogens, what's one way that you could link it all together? Okay, but how would you link the carbons? What could you do? These are alkanes. There's no double bonds or triple bonds, all single bonds. So what could you do? Okay, so to put them all in a straight line. Okay, so let's do first all just straight line. 1, 2, 3, 4, 5. Remember with alkanes, there's always a hydrogen above and below, and then there's one on either end. So it's always twice as many hydrogens plus 2. So you can see that as well. Twice as many hydrogens plus 2 is the formula. So this is what? A carbon with 5 in a row. Nothing else. 5. Right. Butane's 4. Butane's is the weird one. Okay, so that's one. So what's another way I could draw it? What else can I draw with 5 carbons and make a different molecule? That's the Lewis structure. Not so much like thinking about this, draw a Lewis structure, but make a different molecule. Okay, so 1, 2, 3, 4, 5. So I could put 4 carbons in a row and 1 carbon hanging off of a middle carbon. One, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 hydrogens. Okay. Ooh. That is what? Longest chain is a butane. The group hanging off is that's a methyl, and it's hanging off of carbon number 2. So, are these conformational isomers or structural isomers? These are structural isomers. Structural isomers, they have different names. And can you see that they're put together different? One's 5 in a row, one is 4 in a row, and 1 branch hanging off. I can make one more structural isomer. How else could I do it?
Can you make it as a propane?
Yeah, make a propane. And what am I going to do with the other carbons?
Branch off the second one and third.
Okay, so put one here and one here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Still have those 12 hydrogens.
What is the conflict with carbon sharing out hydrogen in the middle?
No, they each have their own.
Okay.
I'll try and squeeze them out. Oh, can you see that? So those 2 carbons sticking up, they each have their own, so each one has the CH3. They each have their own hydrogen. So what would this one be called? What's the longest carbon chain? Okay, is a butane. And then what's this group hanging off? And it's hanging off of carbon. So what did I make? Those are conformational isomers. Can you see that? So 2-methylbutane, 2-methylbutane, just drawn differently, look different, but they have the same name. When you went to do the naming, if the name's the same, then these are conformational. So let's go back to that propane idea. So we're going to have 3 carbons in a row. Where else could you put the carbons that would be different and not create a 4 in a row?
Branch them off each other, branch them off the second one, and then branch one off it.
So go this way.
Yeah.
Can you see that that's?
'Cause it gets
Can you
rid
see
of,
that's 2-methylbutane?
Yeah.
What about the first and the third one?
Where else could I put it? I have to put one more carbon in. If I put one on this side, that's going to make a butane. If I put one on this side, that's going to make a butane.
Put it off the first.
If I put it down here, that's still going to make a butane. Can you see that's 4?
On the bottom.
Right here. How's that look compared to these other ones? Are they different? So in here, this is going to be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So the hydrogens, like all the corners, are H's. They're all CH3s, CH3s, CH3s. There. So if you count, you should still see 12 hydrogens. 3 hydrogens on the top, 3 hydrogens on the bottom, 3 hydrogens on the right, 3 hydrogens on the left. So there's still 12. I got 5 carbons. What's the name of this one? Longest carbon chain makes it a propane. And then this group is a and this group is a methyl. And they're both off of carbon 2. So I would call this 2, 2 dimethylpropane. Should be closer together. All 3 of those, pentane, 2-methylbutane, and 2,2-dimethylpropane, they are all structural isomers. They all have the same formula. They all have 5 carbons and 12 hydrogens, but they're put together differently. And it's really the carbons that are put together differently. Because can the hydrogens be put together differently? No, because they only ever have a single bond. So it's really kind of looking at how the carbons are put together when you're doing this to really be able to see that structural difference. So what about these? Are these structural, conformational, or not related? So they have to be isomers if they have the same formula. So first, count the number of carbons in the top one. Okay, so it's C8, and I'll just tell you it is H18, because you can tell they're all single bonds. It has to have 18. So what about the bottom one? Count the total number. So that's 1 and that's the other.
Oh,
8. Okay, so C8. I was like, what? Did I do this wrong? All right, so they have the same formula, so they have to be isomers. So we know that they're not related. They're going to be related. They have the same formula. So they're either structural or conformational. So the next trick is to name them. So what is the longest carbon chain in the top one? 6. And so where will you start your...
From the left and go down to the bottom.
Far left and go down. Okay, so if it's 6, that makes it a hexane. This is a okay, what about my numbering? From the right, from the bottom, from the left, from the bottom, or does it not matter?
It doesn't matter.
Can you see it doesn't matter? Because if I start from that side, it's going to be 3 and 4. If I start from the bottom, it'll be 3 and 4. So either way, doesn't really matter which way. 3, 4, 5, and 6. So this one will be a 3. This one will be a 4. 3, 4. Dimethylhexane. So what about the bottom one? What's its name? This is a. And so this one is.
3,4 bimethyl.
So these are conformational isomers. When you first looked at them, did you think they were? They look different. And it's just because of the bend in it. Okay? So always go through, first check and see how many carbons and hydrogens. If you have the same number, then you know that it's an isomer. And then the issue is just name them. If they have the same name, they're conformational isomers. They're the same molecule drawn differently. If they're different names, then they're structural. They're actually put together differently.
So make sure you count your carbons by so first, right?
Yeah, just count it. And I'll tell you, like, count your carbons, because the hydrogens are always going to be times 2 plus 2.
Right.
It'll always be that way. You're not going to end up finding something different. So just compare the number of carbons, because that's going to be really the key thing. Okay, so what about the top? Are these?
8 carbons.
Okay, so 1, 2, 3, 4, 5, 6, 7, 8. I put little black dots, so we know this is C8. Okay, what about the other one? 1, 2, 3, 4, 5, 6, 7, 8, 9. Do you see 9? 1, 2, 4. Yes? So you would say these are not related. Okay, one has 8 carbons, one has 9 carbons. They have no isomer connection. They have to have the same number of carbons. That one has bromine, so they would both have to have 1 bromine each too. So if you saw one had a bromine and one didn't have a bromine, then they would be not related and you just move on. What about down at the bottom? I don't know, what is this?
Oh, that's it.
Well, it's just sticking there. Hold on. Just not like, I don't, no, I mean like, why? That's my question. Why did I put that there? Okay, so just squiggle that out. It's like a random chlorine was floating around. 1, 2, 3, 4, 5. 10 carbons. And 1 chlorine. And what about the other one? Can you see 10? And you see 1 chlorine? Okay, so now you know these are isomers of some sort. And they have 21 hydrogens. But if you see that, it'll be that you'll know. If the carbon numbers and any halogen numbers are the same, then it's an isomer. So name that first one. Looks kind of complicated. What's the longest? 7. So 7. Where did you start from? The left, and then go down. Do you see 7? So that makes it a heptane. Yeah, that's what I meant. Where's your chart? It's right there. She always looks at me, she's like, that's a butane? No, propane. Oh. Okay, so now this is a methyl. This is a ethyl. And this is a chloro. So, which way would you start numbering from? This one's I don't.
It doesn't matter.
Really doesn't matter, but since the first non-hydrogen branch, I would take the alphabetical issue. So which one would you start from? Start from the chloro. Okay, since chloro alphabetically, if they're equal on either side coming in, so you see they're both off of the second carbon. So start with the one with the chloro, 1, 2, 3, because that will put your order straight. 6, 7. So this is 2 chloro and 4 ethyl and 6 methyl. Listing them: 2 chloro, 4 ethyl, 6 methyl, heptane. See, if I just asked you to identify that last class, you'd be like, what? Now you're like, simple. What about the next one, though? Where do you got to go from? And how many do you see? Okay, so it is a heptane. So look, here is a methyl. So which way do you start numbering? So you're going to start 2. So 1, 2, 3. This is a 4, 5, and 6. So they have the exact same name. So initially, that makes these conformational. Oh. I know they're kind of fun. Like you get, and it's the practice of it. Like just consistently every time, do the same steps. Don't skip steps or anything. Just do the steps every single time and they'll fall right in because they really do follow right along. Last kind of isomer is cis and trans. You only see this if you have ring structures because the ring creates a rigid structure. So remember so if you take the balls and sticks, they'll all rotate if they're single bonds. You have free rotation as single bonds, but when you make a ring structure, that is going to, now suddenly it is impossible for those molecules to move. So that can create hanging groups, non-hydrogen groups, that are actually like stuck in position. So if you're looking at a ring and one group hangs down, the other group is sticking upward. No matter how you turn that ring around, you can't make them both on the same side. So when they're like that, they call that trans. That means that the non-hydrogen groups are on opposite sides of each other. But notice with the second one, see these two groups, how they're both sticking down? So they're both sticking down, and if I flipped it around, they'd look like they're both sticking up. This one, one's sticking up and one's sticking down. They call that cis. So you add that in front of the name to indicate the position of those non-hydrogen groups, and you're really only going to see it in a ring because we don't even name double bonds. We don't do any of those. So that's really the only time you're going to see it. So you will see the wedge and the dash. If you see two wedges, remember that means they're on the same side. If you see two dashes, it means they're on the same side. But if you see a wedge and a dash, remember that means that one's pointing forward and one's pointing back, that they're on opposite sides. So this one would be trans 1,2 di what? Dimethyl. And the ring of 5 is cyclopentane, so the cyclo, right? That ring, you've got to put a cyclo in there, it means ring of 5. The next one, the one on the right, would have the exact same name, except instead of trans, you would put cis in front.
It'll be drawn like that on
Yes,
the test?
you will see it that way
So
because
like
it's hard to see it otherwise. Now they do sometimes draw them like that, and so you'll see one sticking up and one sticking down. Okay, so if you didn't have the wedge and the dash, you would see that there one like the methyl group would be sticking up and a methyl group sticking down. So that one on the left would be trans. And I always think of trans as like on opposite or across, like you go trans America, you go across America. So I always think of it like that. Whereas I always say like cis means the same. Cis is on the same side. So the cis and the letter, the sound of the word, cis is same. So they're both going to be pointing down or they're both going to be pointing up. And you're only going to see that in the cycloalkane rings. It does exist in other molecules, but for our naming, that's all you're ever going to see them as. They call these stereoisomers because, in fact, they have the same formula and they have the same basic name, but you have to identify the non-hydrogen group as being in an up or down position, as being together on the same side or on opposite sides. They just have a different, what they call a spatial arrangement. Well, we can start them. All right, so this is the next to the last topic. We have functional groups and chiral carbons, and we're done with chapter 4. Thank God. Okay, so functional groups, and we actually talk about them a little bit. If you've done your pre-lab for lab 7, functional groups were one of the things that you had to identify. So a functional group is just a group other than single bonded carbons and hydrogen. Okay, so the single bonds of carbons and hydrogen, those are the ones they just call them alkanes. So it just means all carbons and hydrogens and all single bonds between the carbons. But you can have double bonds between carbons. They call those groups alkenes. Okay, so the difference between an alkane and an alkene is just that alkanes are all single bonds. They sometimes call these the saturated molecules.
That's the alkane.
Alkanes are all single bonds, whereas alkenes can have one or more double bonds. These are the ones that are unsaturated. So when we talk about saturated and unsaturated lipids or fats and oils, it is actually their carbon-to-carbon bonds that causes them to look different. So a fat at room temperature compared to an oil, fats are what? Bacon grease, butter, lard. How do they look at room temperature?
Like grease, like
They're solids, right? And so they're the saturated fats, okay? Fats are saturated. They're almost all single carbon-to-carbon bonds, and they can pack in really tightly at room temperature, and that's why they're solid. Most of those fats come from animal sources. So most of them are like bacon, grease, lard, that's all from pigs. Then you can get butter, that's the fat from cows. So that's most of yours are animal fats. They're solid at room temperature, all single carbon-to-carbon bonds. They're alkanes. Oils, though, have one or more double bonds. So oils are called unsaturated, and if you have monounsaturated, it means you only have one carbon double bonded to a carbon. If you have polyunsaturated, poly means many. It really just means more than one. So poly would be more than one double bond. Those are things like vegetable oil, canola oil, olive oil, peanut oil. Those typically come from plants compared to animals. And at room temperature, those are usually liquids. And it's because of that bond difference that allows that variation. So in the unsaturated, we have these alkenes. These would be the oils. There's one other type. Those are called alkynes. Those are actually carbon triple bond to carbons. They're also considered unsaturated because they have multiple bonds. The unsaturated are more reactive than the saturated. So the more, when you have double bonds and triple bonds, that's going to create a more reactive molecule. It's not as stable. Single bonds are the most stable. So alkanes are more stable. Than alkenes with their double bonds. And alkenes are more stable than alkynes with the triple bonds. But those are just variations that you can see between the carbon-to-carbon bonds. So there's one. That one shows an alkene. So you can see there's a carbon double bonded to a carbon. This one's ethene. Ethene is actually the chemical that's released by fruit as it ripens, and it triggers ripening of other fruit. So that's why, like bananas, if you have bananas in a bunch, they'll actually ripen better if you have just a single banana. It's actually a lab we're going to do next week, looking at the ripening process of fruit and how that breaks down from a polysaccharide to a monosaccharide. We're also going to look at this tonight. So this is when you have a 6-membered carbon ring, so 6 carbons. Instead of them all being single bonds, that would be a cyclohexane, right? If you had 6 carbons in a chain or in a ring, it would be a cyclohexane. But this one actually has a single bond, then a double bond, then a single bond, then a double bond. So that alternating actually gives it a little bit different characteristic. They call these the aromatics. They called them that because when they first started studying them, they were like, oh, they're kind of smelly. So they said that they were aromatic in scent because they had kind of nice smelling scents to them. I don't know, phenol doesn't really smell all that good to me, but depends. A lot of like benzene is one that you find in gasoline, so it's some of that type of smells. So that, if you saw it in a skeletal structure, it looks like a ring with like single, double all the way around.
So it's single,
Mm-hmm. And because of that, you can see that each carbon only has one hydrogen, because each carbon has a double bond and a single bond, and so there's one extra bond to make it 4, so there's just a single hydrogen hanging off of each one. So that one's called the aromatic. Sometimes, and I don't do it as much, but sometimes you'll see in a book, you'll see the hexagon shape, and you'll see like a circle inside. So what that's saying is it's because the single double bonds create a pretty stable molecule, and so they'll sometimes draw it like that because it flips back and forth. So sometimes the double bond's like on the upper right, and sometimes the double bond flips over to the upper left. So they kind of flip back and forth, and so you'll sometimes see it with a little circle in the center. Same thing. All of those would be considered that aromatic, that single and double bond alternating in that 6-membered ring. So there's the 4. These are nothing but like functional groups as in terms of the hydrocarbons, because nothing but carbon and hydrogen in these. Most of the ones that we've been naming, those are all alkanes. And we actually aren't going to name alkenes, alkynes, or any of the aromatics. We're not going to name them. All you have to do is just like, if you look and you see that there's a double bond, you say, oh, that's an alkene. Okay? That's all you have to identify. You don't have to be able to name it other than just to identify it as that kind of group. If you see a triple bond, then you know it's an alkyne. And if you see that alternating single and double bond arrangement, that's an aromatic. So the only other functional groups are those that contain nitrogen and or oxygen. So one of them are alcohols. So most people are familiar with rubbing alcohol. Okay, which is isopropyl alcohol, or vodka, which is ethanol. Okay, so that's another alcohol. Alcohols always have this. They have a carbon, and then there's an OH hanging off. So you could have that OH off of the middle carbon. You can have the OH off of an end carbon. If you have nothing but just an OH, they call that an alcohol. An aldehyde, on the other hand, is when you have an oxygen, and it looks like the alcohol flipped backwards, but what that's actually showing is that you have CH3, CH2, a carbon double bonded to an oxygen, and then a hydrogen. So looking at that structure, CH3, CH2, then the next carbon has a hydrogen attached to it and a double bonded oxygen. So see how those two are different. So remember formaldehyde, that is one of the molecules that we like drew when we were doing the covalent bonds. Formaldehyde is the smallest of the aldehydes. That was the one that looks like a trigonal planar shape. It had that double bond oxygen and 2 single hydrogens. If you have a carbon in it, this one, aldehydes are always on the end of the molecule. Alcohols can be anywhere. They could be in the middle or they could be on an end carbon, but aldehydes are always going to be on an end because they're going to have a carbon double bonded to an oxygen and a hydrogen. So the chain's not going to go any further. Carboxylic acids, they look a little like an aldehyde, except they have an extra oxygen. So this one, this is what vinegar is. So we're going to use this in lab tonight. So this is 2 oxygens on an end carbon. One of them is double bonded, the other one's like an alcohol. So those 2 together create your carboxylic acid. This is acetic acid, which is vinegar. This is always on the end of a molecule. You won't find a carboxylic acid in the middle of a molecule. The nitrogen groups, just 2 of them. The nitrogens are either going to be amines or amides. If they're an amine, then they have just carbon and nitrogen. So there's just carbons, and then there's going to be a nitrogen attached to just carbons. So in this one, it comes out CH3, CH2. Those are just normal, CH2. And then you have the nitrogen with its hydrogens. Remember that nitrogen only has 3 covalent bonds, so it's connected to a carbon, and then it's going to have 2 other connections. But that's all. That's an amine. Amines are kind of stinky. Amines are like your fishy kind of smells. Nitrogen is a type of amine, so that's like the smallest of the amines. It's just a pure nitrogen. When stuff begins to break down, proteins begin to create all of these strange amines. There's putrescine. Have you ever ridden by like something dead on the side of the road and you're like, that's all of the amines that occur when muscle tissue and proteins begin to break down. You end up with a lot of these that are formed, and they're super smelly. But amides have this. So instead of just a nitrogen, they are actually connected to an oxygen as well. So this one is a CH3, CH2, C. Then you've got an oxygen, it's here, an oxygen connected to the carbon that then is connected to a nitrogen. And then the chain continues. So amides are always in the middle. You'll never find an amide on an end. Amides are always going to be like in the middle of a chain. This is actually what holds proteins together. Amino acids get linked together by forming a link between the carbon on one side, which has an oxygen, and a nitrogen on another side. They get linked together in order to form long chains of protein. Ketones. So ketones look kind of like an aldehyde, except that instead of being on an end, ketones are kind of like amides. They're always in the middle of the chain. Next week, we'll use acetone in lab. We'll use it to dry our starch. Acetone's like nail polish remover, and that's actually what that molecule is. Always in the middle, though. Ketones will never be on an end. Ethers show what happens within how oxygen can form kind of like a link within a carbon chain. So you can have carbons, 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 then you can have an oxygen. And it single bonds to another group of carbons. So you can have carbons on either end with an oxygen link. Remember, oxygen only ever forms those 2 covalent bonds, but that means that it can actually become part of the chain. Hydrogen can't. Hydrogen's never in like a linker. Hydrogen's always on an outside, but oxygen can be. So oxygen is an ether. Ethers were kind of interesting. Those were early anesthetics. So they would take and like put the ether, that usually it was like dimethyl ether. They would put it on a cloth and they'd be like, here, inhale this. And so you'd be like, and it'd knock you out. Like that's what they used to, whenever you saw people like getting kidnapped, that's what they like chloroform them. So that was an ether to knock them out. They lose consciousness. Extremely flammable though. So I'm not really sure how that always worked out so well. But ethers. Esters look a lot like an ether, except that they have like a ketone with them. They almost look kind of like a ketone and an ether put together. So you have a carbon with a double bonded oxygen and an oxygen linking it to another carbon. So again, these are in the middle of a chain, just like the ether is, always found in the middle, never on an end. And you see how an ester looks kind of like a ketone and an ether put together. Esters are really nice smelling. All of your fruit flavorings, those are all esters. So like your banana and apple and pear, like ripe fruit smells, those are all esters. Thiols are kind of unique. You don't see them a whole lot, but these are if you have a sulfur contained within an organic molecule. Sulfurs are sometimes found in proteins. Thiols tend to be kind of smelly, like swampy, sort of smelly, or like they say, like the egg kind of smell, that sort of sulfurous smell, like kind of jungle sort of smell. So that, like that sulfur kind of gas that gets released when material starts to break down, that's what a sulfur looks like, kind of like smells like. But it's called a thiol, and it's just if you have a sulfur anywhere in the molecule. Another one we're going to work with tonight is a phenol. And a phenol looks like an aromatic and an alcohol. So it looks like that 6-membered ring, that alternating single and double bonds, and then has the alcohol group on it as well. By itself, it's a good disinfectant. Some medications and some living tissue actually use phenol groups. It's a problem with ingesting some of these types of phenol groups, and we'll talk about the effect that actually had. We're doing aspirin in lab tonight. Whew. So I wanted to introduce them. Pages 138, 139, and 140. This is in chapter 4. Go through and look at those. Look at those charts. Have this is like another handout that you'll get with the test, and this is actually kind of like a summary of the functional groups. Next time we'll go through trying to identify functional groups, non-carbon hydrogen groups in some of the organic molecules. You don't have to name them, you really only have to pick them out. Like you have to be able to pick out an alcohol, pick out an amine, pick out an ester, pick out an ether, pick out a thiol, but you'll have this chart to be able to use and be able to refer to. So kind of keep that, I'll pick them up, but I'll give them back to you so that next time you can look at them. And if you want to look at that chart, I did put like a Word version of that chart on Moodle as well. So we'll pick back up there next time.